All right. Good morning. Welcome all. My name is Tristan Bereau. On behalf of LS Institute Data Science Seminar, I'd like to welcome you all. And I'm very happy Tristan with us today. Tristan Bereau studied at EPF, earned his PhD at CMU, went for postdoc in Basel, was a group leader at MPI, emulator group leader, then assistant professor in Amsterdam, then worked accepted a call for a company working in cryptocurrency. And finally, and luckily, came to Heidelberg, where he has been since 1st of May. And he has already taken a very active role in shaping the Future of Excellence cluster. We're super happy to have you here, Tristan, and glad to hear more about your work today.
All right, thank you so much. It's a great pleasure to be here. I'm excited to be here. Thanks to Fred and thanks to the LS unit for the invitation. I'm going to talk a little bit about molecular discovery and molecular optimization. And to do this, I'm going to sort of separate the talks into two parts, one shorter, one a bit longer. And I'll start with doing molecular optimization starting from experiments, which I think is something that, not sure it's simpler, but at least it's something that's we're probably more, we think about more, we've been thinking about a bit longer. And so it's something that's a bit more common to think about. But then I'd like to move into generating our own synthetic data from computer simulations to then do the whole pipeline sort of in silico. And then really sort of like the end goal being trying to guide the design and suggest molecules and compounds purely from computational grounds. And I'm going to put this back in. And so I'll show these two pictures, and so they're going to sort of motivate a bit of the ideas I'm going to talk about, especially for the synthetic part, for the in silico part. And so on the left, I'm showing a sort of cartoon picture of chemical space, so chemical compound space, which I'll refer to as the space of all possible molecules. And here, because we're going to talk a little bit about sort of bio applications and sort of drug design type applications, I'll talk about the space of small molecules, small organic molecules, which is in itself is a huge space of compounds. It's astronomically large. And on the right, I'm like to motivate the idea of so-called coarse graining, sort of working with simpler, effective models. And so I'm using this picture of this Lego representation of the self-portrait of Van Gogh, which in itself is a coarse-grained version of the picture of Van Gogh. And so there's like two levels of coarse graining happening in this picture. And so we're going to be applying these ideas loosely to molecular simulations and molecular modeling. And so in terms of like working with simple, effective models for molecular systems. This doesn't really work very well. Okay. Right. Okay. So before I start, let me thank the people who did the work. In particular, I'd like to thank Argo Dutta, who worked on the experimental part I'll show at the beginning, Karen Kaneko and Roberto Menichetti, who really work on the sort of the foundations of the ideas I'll talk about. Mark Stiefenhofer on the backmapping, which I'll get into a little bit. And then Bernadette Moore did a fantastic job in the molecular design applications. And so we're working with sort of materials and condensed matter, and particular soft matter. And soft matter has the tendency. So soft matter means we work with sort of materials that are soft. So the characteristic energy is kT, so it's thermal energy. And so at thermal energy, you have so thermal effects are responsible for a variety of phenomena. You think about soap bubbles and protein folding. These are all effects that are sort of coming from soft matter and due to thermal effects. And what it means that there's sort of relatively poor scale separation, which makes it difficult for us to model. And you have sort of a hierarchy of behavior happening. If you go from the chemistry of how you prepare your sample to the building blocks, and this goes a little bit into sort of really like coarse-grained or mesoscopic building blocks, to mesoscopic structure, and then sort of microscopic properties, which you'd be able to measure in the lab, even possibly observe directly with your own eyes. And so if you think about preparing a sample, you have sort of making a measurement is sort of a forward approach of going from your chemistry to the related properties. In general, if we're thinking about design or thinking about extracting some sort of relationship, we're typically interested in the inverse approach, which means I would like to have a certain property. What is the chemistry that's relevant for me to sort of have a certain property or optimize for a certain property? And this is notorious as an inverse problem. And so this is something that's notoriously ill-defined and mathematically difficult to solve in closed form. And so this is going to introduce a lot of the ideas of inductive approaches and introduce ideas of machine learning. And so that sort of naturally introduces the concept of, because it's inductive, then we introduce the idea of it's very data driven, that you want to have many examples to base your model on. And so there's this sort of additional scale that comes in terms of how many compounds you're able to work with. And it's very clear that depending on the situation, whether you make your measurements, whether these are experimental measurements or measurements on the computer, whether you do this by hand and then you're going to be limited by doing this for a handful of compounds, or if you manage to sort of systematically do this and scale it up in terms of the number of compounds, that you do a so-called high throughput screening approach. And this is something that's very much of use in many applications. Experimentally, it's been heavily developed over the last decades in various areas. If you think about drug design, a lot of these sort of high throughput cell screening assays exist and are used on a daily basis. And of course, it makes sense that the more compounds you have access to, the more data you have. And so the type of statistical modeling you'll be able to do on these data points is going to be different. It will open up different ways of doing statistical modeling. And so, by the way, there's like this systematic approach, means that in each test tube, what ideally is happening here is that you have an environment, maybe a protein with a solvent, and then you're going to insert a small molecule, and then in each test tube, you're going to have a different small molecule. Right? But the environment should stay the same and the conditions should stay the same. So that you do very systematic measurements, only changing the small molecule to screen across this small molecule. All right, and so when it comes to molecular optimization, we work a bit we have a bit of an unfortunate situation in that we have a combination of sort of two pieces of bad news. One is that chemical space is relatively high dimensional, and it's a high dimensional space, which makes any sort of interpolation or search or clustering difficult to begin with. And this is compounded with the even worse news that we typically work in a low data regime. So data is expensive, it's difficult to get. Whether you work with experiments or with computations, data is sort of typically the bottleneck. And so that means that you have to play tricks in order to work in a high dimensional space with few data points to begin with. And so a very successful idea has been to, instead of working directly in this original high dimensional space, to project it down into a lower dimensional latent space. And so that's been very successful. There are many examples, particularly this one here, which starts from a sort of subset of chemical space of many molecules, and then pipe this through a variational autoencoder to then learn a latent space and then do molecular optimization in this latent space. And this is a lot simpler than doing it in the original high dimensional space, especially if you have very few labeled data points. We typically work in a situation where we have many unlabeled data points and very few labeled data points. And so that this makes these types of sort of semi-supervised learning approaches very appealing. So let me show an example in terms of design from experimental methods where we work with viral infectivity peptides. So these are peptides that may form, we're looking for peptides that may form fibrils and that may have an impact on viral infectivity. And this was working with the HIV-1 system. And so we had experimental colleagues who had a relatively small data set of about 160 peptides for which they had assay measurements for these systems. And so the idea here is the same, in that instead of working directly with these peptides, we sort of encode them using this protein vector embedding, which was sort of pre-trained to give us a low-dimensional representation of protein sequence fragments. And this allows you to sort of combine small fragment triplets in terms of vectors, which you can easily sum up to then get a representation. And here it's this 100-dimensional space. So you have a low-dimensional, 100-dimensional space for these proteins. And then the idea is to work starting from this type of representation as a starting point to do any analysis. So from this, we can build surrogate models to try to learn directly and predict the infectivity. And you can see we can do this relatively well. And then we can also do unsupervised learning to try to sort of scan the space of compounds that we have. And so in gray here, we have the training set. You see we have very few points here, very clustered. And then in blue, we have prediction. So we do this over a much larger subset. And then we selected points in yellow here, which we then tested in the lab. And this would then experimentally characterize. And this makes a point for the use of these low-dimensional representations to both build surrogate models for supervised learning and then to navigate sequence space and across, say, diversity and structure property using unsupervised learning. And so the question is, can you do this with computer simulation? So this was, as you see, that the labeling of these data points is from experiments. And so really the question here is to do this from computer simulation, so doing this in silico. And so we start from the idea of multiscale modeling, which is sort of a prevalent idea in any sort of materials modeling, in that we don't have computers that are fast enough to run everything from first principles and with the best possible accuracy, which would be from quantum mechanics, which has many different flavors actually. But so we will make a number of simplifications to be able to reach larger length and time scales. You can see on this plot here. And so, for instance, we go from quantum mechanics to particle-based classical mechanics, like molecular dynamics. And then you can go all the way to continuum mechanics, things like partial differential equations. And so you have a large array of methods you can use in order to target a particular type of length and time scales. And so that's going to be the workhorse we use in terms of modeling. And then the question is, depending on the length and time scales you're interested in, that will guide the type of modeling you will use. And so I'll argue there is sort of a two-way street going on between the exploration of chemical space and multi-scale modeling. So on the one hand, you know, the older picture of doing materials modeling has been to focus on one or a few compounds. And so, and if instead you look at it in a context of exploring chemical space, so you have a more holistic approach or a holistic view in terms of trying to model all of these compounds, it creates different constraints and a different mindset in terms of parameterizing your models, how you run your simulations, and how you analyze them. And so it's creating a slightly different perspective. On the other hand, and this is something I'll argue here, multi-scale modeling allows us to more efficiently explore chemical space. And so it's something I'd like to get into, but there is something about the types of scale separation provided by the physics that we understand that we can use and exploit in sampling and navigating chemical space. Okay, and so this idea of coarse graining is not something that's completely arbitrary and has no basis. It's started from scale separation, which is sort of a strong, deep, and rigorous framework in a lot of in much of physics. If you start from renormalization group theory, in polymer physics, we have things such as the blob picture, which really sort of encodes this renormalization group theory to polymers. You can see this picture here, and this leads to things like scaling concepts. And this has been sort of first theoretical and then led later on then sort of applied in terms of computer simulations. You know, and this was maybe 30, 40, 50 years ago already. And so to give you an example, sort of an early example of what this meant, I think this is an interesting application here where these people started from this, so this polymer, which is a polycarbonate melt here. So you can see the chemical structure there. And they wanted to, and so the computers were not fast enough to model a large polymer melt with atomistic detail. And so it was very common to work with effective model. So here, this is a very simple bead spring model, a bit of a toy model that is trying its best to reproduce the behavior of the original system, right? So you map this the atomistic resolution here into a toy model made of beads and springs. And the way they were trying to encode for these to map these is by encoding the Boltzmann distribution, mapping the Boltzmann or projecting the Boltzmann distribution of the atomistic degrees of freedom into these coarse-grained beads here. And that's been sort of a prevailing idea that stayed in the field. That was the beginning of structure-based modeling. So starting from the microscopic information from the underlying chemistry, and then directly trying to connect to experiments. So you can see here viscosity, which is a very important materials property for these polymers as a function of temperature. And you can see here the bridging between the simulations and the experiments. And so it really sort of started the field in terms of materials modeling and trying to bridge between experiments and simulations. And these models, these effective models, so they throw away a lot of details, right? They're extremely simplified. What they try to do really is sort of if this is a pictorial view of the free energy landscape, so the landscape of all conformations, this is in particular for in the context of protein folding, where you may have one well-defined native structure which would be sitting at the free energy minimum or representing the free energy minimum. Coarse-graining allows you to sort of, roughly speaking, reduce that conformational space and makes it smaller and makes it more navigable and easier to navigate. And so that means that things such as self-assembly really mean you're sort of falling down this free energy landscape, and you can do this more effectively and more efficiently with a simpler coarse-grained model. And so what we have here is a bit of a compounding problem, because if we start thinking about these types of ideas in the context of exploring chemical space, then you can see that we have this for each system, we have this free energy landscape that we're trying to explore and self-assemble a system so that we get the most likely structures. But we're doing this for every possible point in that chemical space here. And so where every point here is a molecule. And so you have a large space here, and for each point, there is a large space in it. And so you're compounding two problems of exploration. And so that's the bad news, in that it makes it computationally difficult. The good news is that there's sort of relatively similar-ish type of important sampling problems. And so from a statistical mechanics perspective, you can approach them in similar ways, at least in terms of philosophies. And so the type of coarse-graining I'm going to talk about will look like this. And so it's again, these types of simple bead spring models that I showed you for polymers. Here I'm going to focus more on small molecules in more sort of biotype environments. I'll get to this. But so this is the type of course, nobody tells you how much you want to coarse grain. This is up to you. And so this is the type of coarse graining we'll work with here. And so more or less at the level of let's say a chemical fragment. So a few heavy atoms that will lump into one coarse grain bead. And so we'll have these larger particles. And what we're going to do is, instead of working with sort of atomistic molecular dynamics, where you would integrate Newton's equations of motion for every single atom here, we will do this, but only for the larger particles, the larger beads here. And we'll integrate Newton's equations of motion for the beads. And so whether that works or not completely depends on the quality of the model and the parameterization and all the assumptions you put into these models, and how commensurate they are with the types of the driving forces of the problem at hand. And so again, so this reduction in the conformational space, which allows you to sample the phase space or conformational space more easily, is really due to the reduction of the structural. So it's due to the structural mapping. So the reduction in the number of degrees of freedom, right? You go from many atoms to fewer superparticles or beads. this idea of reducing chemical space is not actually something that works for all coarse-grained models. It's something that works for so-called transferable coarse-grained models. And these are models that have a discrete set and well-defined sort of bead types. So that you encode particular physical chemical characteristics in each color. It's like working with Lego blocks and colors, and you only have a finite set of Lego blocks and colors. And if I ask you to build a molecule with this finite set of Lego blocks and colors, then you will have to make some compromises. And so you're effectively projecting down into this basis set of bead types with particular physical chemical properties. And so that leads to sort of inaccuracies because you're making your projection discrete. But because you make it discrete, it also means that two molecules that are very similar may end up having the same coarse-grained representation because you don't have enough resolution in your beads or your Lego blocks in order to distinguish them. And so what it means is that it introduces degeneracy in your chemical space, which inherently sort of makes it smaller. So you end up having a chemical space where you lump molecules together because you cannot tell them apart, and so you reduce the space. And so because you reduce the space, it's going to be easier to navigate it. And so that's going to be the interesting idea there from these coarse-grained models. And so if that's so, then you can sort of relatively easily convince yourself that the way to change how much you compress this chemical space, how much you reduce it, has actually nothing to do with the mapping, so the reduction in the number of degrees of freedom, but it has to do with the number of bead types that you use. So how many colors you allow your model to have. And so the fewer the colors, the smaller the space, because the more molecules will get mapped onto the same point. And so this is how we can sort of then play and sort of systematically reduce or sort of increase back the size of chemical space. Now, before I go to applications, there's a very important and serious aspect of going back, right? So as you can imagine, we're going to sort of run simulations at this level. We're going to extract properties. We're going to make predictions. And then the idea is, well, how relevant is that? And then what type of molecule, what type of chemical structure would that correspond to? And so this relates to the idea of reintroducing degrees of freedom. And as much as sort of removing degrees of freedom, so this forward approach of coarse graining means you're removing degrees of freedom, that's always easy. You can always remove them and sort of project down and marginalize. That's easier. But if you want to reintroduce degrees of freedom, then you have to get more information out of nowhere. And so this gets a little bit more difficult. And so one aspect we've been toying with is the idea of working with generative models. And for instance, here, generative adversarial networks, where you would start from random noise, and then you have a generator network that would create, so here in this case, an image, and then you have a discriminator that is trying to tell apart whether the image is real or fake as a classifier. Here, what we can do is instead of having images, we can have molecular configurations, and we can make it we can make the generator conditional on the coarse-grained degrees of freedom. And so we start from noise, go to and create an atomistically resolved molecule conditional on the coarse-grained degrees of freedom that's given to us. And so in some sense, what we're trying to do is learn the probability distribution, the probability density of the atomistic coordinates given or conditional on the coarse-grained degrees of freedom. And so we tried this on a different type of system. It's a polymer again, polymer melt, in which we trained on a melt, so in a liquid. And so you can see here this G of R, which is a pair distribution function. So it's a pairwise distribution function between atoms. And so this is a measure of figure of merit at the atomistic level, not the coarse grain. And you can see very good agreement. If we take this same model and then cross the phase transition without retraining into the crystalline state, you can see we still really we have excellent reproduction here as well, which is quite remarkable. And it probably says something about the fact that we didn't need to retrain the model at all. So the model did not know anything about the crystalline state. And these configurations are quite different. And so the fact that it works so well probably tells you that there's a scale separation happening of the coarse-grained model taking care of a lot of the structural aspects of the sort of longer range interactions, so this rearrangement. And then the generative model is only responsible for the local rearrangement that's probably a lot more transferable between different phases of this polymer system. We can do this for chemical transferability. It doesn't work quite as well. And so I think there's still some work to do in order to improve the agreement here. But the upshot here is that we can then start from these generated structures and run molecular dynamics without equilibration. These samples correspond to the Boltzmann distribution. All right. So let me go back to coarse graining. I'm going to get into applications. So we're going to work with so-called top-down models. So top-down means we don't start from the microscopic information, but instead we start from the sort of long-range physics. So we start from phenomenological information. In particular, for these types of sort of soft matter biosystems, a big driving force is hydrophobicity and things like hydrophobicity and charges, right? That leads a lot to the partitioning. If you think about oil-water mixing, it's heavy. The main driving force is this. And so that's the type of sort of physical interactions we want to imprint. And so our coarse-grained model is not going to be able to do much, but at least it will have the right thermodynamics of partitioning between different media. And so in terms of applications, we're going to be focusing on phospholipid membranes, right? So this is a cartoon picture at the coarse-grained level of a phospholipid membrane. So this is a model membrane for the cell. So the cell membrane, which is what creates the wall between the cell and the outside world. It's made of these long amphipathic molecules called phospholipids, and they have a hydrophobic character here, which is typically repelled from the water, and the water is in white on both sides. And then what I have is a small molecule that's in yellow here. And what I'm going to be interested in is the permeation of this small molecule. So there's no biology here. There's no protein cargo pulling my molecules through the interface. I just have simple thermal fluctuations. And just through thermal fluctuations, there's going to be diffusion, with some rate. And then the rate depends a lot on the chemistry between the small molecule and the phospholipid membrane. And so you can think of this as measuring the flux of the drug across the membrane. We're going to look at this reaction coordinate Z, which is sort of the level 0 of reaction coordinates you could think of. And if you write that down in terms of a Fokker-Planck equation, for instance, you can extract a value for this so-called permeability coefficient, which is an integral over the reaction coordinate. So across this reaction coordinate here of the exponential delta G. And then delta G is the potential of mean force. So that's the free energy of sort of dragging the molecule across, right? And so interestingly, there's no experiments to give you potential of mean force. So computer simulations are the only way right now to get these things. And what we'll do is we'll do this. That's relatively standard. But what we'll do is we're going to screen across the space of small molecules. So we're going to change these small molecules one after the other. And then each time we're going to recalculate this potential of mean force to get the permeability coefficient. So this is how it looks. We consider a subset of chemical space. We have about 1 million molecules. We coarse grain every single one of them to this coarse grain representation. Because of this reduction of chemical space, we end up with something like between 100 and 1,000 coarse grain representations. For each one of these, we run molecular dynamics, in particular enhanced sampling molecular dynamics simulations. And we can extract these potentials of mean force. And from this, we can then get a permeability coefficient, this equation I showed you before, and we can put this on a low-dimensional map, right, as a function of, say, 2 physical-chemical descriptors. And because we have a value of the permeability coefficient for every single one of these 1 million molecules. So this type of high throughput sort of simulation strategy is similar and inspired by the high-throughput DFT, so density functional theory in quantum chemistry, and so in order to screen across electronic properties. And here we're doing the same thing, but to screen across thermodynamic properties. Here you realize that because we're coarse graining, we're reducing the number of simulations we have to run, and so that leads to a very computationally appealing and computationally sort of low demand in terms of our strategy. It also smoothens a lot of the entire landscape, and so that means that it helps us suggesting low-dimensional representation and structure property relationships in general. We can do a number of things. I'm not going to go too much into detail, but we can do, we can relate. So this is the same plot of this permeability coefficient across sort of chemical fragments. What are important chemical fragments for inverse design? We can try to learn an equation. In terms of biophysics, we can try to relate or find out interesting or important characteristics of these small molecules to drive liquid-liquid phase separation in these membranes, which is something that's biologically important. And I'm not going to talk too much about this. I'll talk about an application more in the context of molecular discovery, because that's what I promised at the beginning. And so I'm going to talk about cardiolipin, which is this sort of beast of a phospholipid. So this is a normal looking phospholipid. This is phosphatidylglycerol. That's very representative of the type of phospholipid you have in your cell membranes. There are hundreds of components that you have, but that's one of them. Cardiolipin is a very large beast. It's found in the inner mitochondrial membrane. There's interest in sort of measuring how much of these cardiolipins you have in your inner mitochondrial membrane. There's several reasons for this. One is aging of the cell, and there's also pathological reasons. So there's interest to get probes that will measure the concentration of this cardiolipin. The problem is, as you can, if you squint a bit and look at it for a second, you'll see that this lipid basically is a dimer of this phosphatidylglycerol. It's about exactly a dimer. It sort of fused there, right? And the problem is that the inner mitochondrial membrane also consists of phosphatidylglycerol. And so if you want to be able to selectively monitor this, you have a bit of an entropic problem, because you want to monitor this and not two of these. And so that's entropy. And so that's difficult, and there's basically no experimental data set in terms of molecular probes that exist to directly do machine learning. There's a few probes have been proposed, but there's hardly any, and so it's not enough to do machine learning on this. And so we're going to try our framework to do this. Yes. And so again, we're going to sort of work with this idea of trying to optimize in a low dimensional space. So like we did in the experimental data problem. And so what happens is that, so I didn't tell you, but the estimated number of small organic molecules is about 10 to the 60. It might be a lot more, it might be a lot less. It's not very clear. But anyway, it's a very large number. When we apply our reduction of chemical space, we end up with about 10 to the 5 coarse-grained representations. And so that's still a lot of compounds to run free energy calculations and molecular dynamics on. So it's still too much. And so what we do is we rely on this idea of learning a low-dimensional latent representation. On these coarse-grained representations, these are not anymore real molecules, or coarse-grained representations. And so then we have an active learning cycle where we go from sort of rigorous free energy calculations to compute this relative stability of a compound in cardiolipin versus the same compound in this sort of baseline phosphatidylglycerol lipid, so the simple one. And then we're going to use the relative free energy difference as a stability measurement. And then we're going to use deep representation learning to learn a latent space, and then train a Gaussian process regression model in the latent space to predict this selectivity value. And so at first we have this for, maybe we started with about 100 compounds, so very few compounds here. And so we have good prediction in some places, bad predictions in others. And then we use Bayesian optimization to tell us where we have poor predictions, and this is going to suggest what new compounds to run and compute this selectivity value for. And then we do this for a few cycles. So what we get from this are design rules in terms of important bead types. And so these bead types, as I told you, they relate to physical-chemical interactions, things such as dispersion and electrostatics. And so we can interpret them in terms of their physical chemistry. And then we use these design rules to then suggest compounds for experiments. And interestingly, 3 were found to be selective in vitro and 1 even in vivo. And I think this is as far as I know, it's the first sort of coarse-grained simulation strategy that was used to design a compound that had any sort of property and efficacy in vivo. And so that's a promising strategy in terms of using very simple toy models in order to do molecular design. And then to finish here, I'd like to go back in this aspect of this representation learning, in that, so what happened here, so this was part of this active learning strategy we had. We started from coarse-grained representations of molecules. So you can see these large beads here. They're shown with their bead types, that's the colors. And then we piped them through a variational encoder. And the problem with this is that it's actually pretty difficult to interpret what these low-dimensional coordinates are. And so it clouds interpretability, and so this is a common problem in machine learning. And so we'd like to get a little bit more insight as to what these coordinates are. And the other aspect that's a bit not so appealing is that if you look at it, we're only providing information about the solute, so only about the small molecule. But of course, the small molecule is not in vacuum. It's sort of embedded in this lipid membrane around water. And so there's a big effect of the environment. And so that's playing a role. And especially the interactions between the solute and the environment are important. And so what we'd like is to reintroduce the information about the environment. If we say we'd like actually to correlate this to the thermodynamics. And the thermodynamics are about the role of the environment. And so to do this, we changed our representation. We're using a representation that's sort of mirroring the idea of structural ordering in molecular liquids in terms of 1, 2, and 3 body interactions. So I told you before about G of R, this pairwise correlation function. You can think about correlation functions that are pairwise, but also you can go to higher orders, and here we look at triplets as well. And so that's going to be sort of a measure to quantify what type of local environment a solute may be experiencing. And then on top of this will be sort of Boltzmann averaging around this representation, because we don't have one particular configuration, but we have a Boltzmann average. So this representation we borrowed it from quantum chemistry. It's called SLATM. We borrowed it from quantum chemistry and applied to molecular liquid theory, and there's actually sort of interesting parallels to be made in order to try to capture both this aspect of working in a condensed phase environment and working in a thermal environment. And if we do this, so we take our solid, we embed it in its environment, and then we compute this representation. Then relating this to our thermodynamic property then becomes super simple. And actually, we can do this even with a linear model. And so we could actually do this very well with principal component analysis, which is a linear model. And the great thing about it is that so not only can we take 2 of the main principal components, and we find a clear separation between low activity and high activity compounds, so sort of high performing compounds and poor performing compounds. But also these principal components are easy to interpret because we can directly sort of invert them and find what are the contributions of different sort of pairs of B types and triplets of B types. So it directly links and gives us information about the relevant physical-chemical interactions. And that's nice in order to sort of extract the physics. And so here, I mean, the take-home message, which is not super surprising, is that if you put more physics into your representation, then it's easier to learn because your representation has captured more of the information. And so it puts more weight on the representation. And so the unsupervised learning has to do less work. And so you can do it with a linear model. Okay, I'm at the end. I'd like to sort of restate again this aspect of this chemical space perspective on modeling, which means we don't start from looking at one particular compound, but we have a more holistic approach at looking at an ensemble of compounds. And that changes quite a bit how we think about, setting up parameterizing, running simulations and analyzing them. And that's actually the same if you look at the quantum chemistry field. And then this contribution of multiscale modeling to explore chemical space, and that so the multiscale modeling that we use, in particular the coarse-graining that we use, is sort of this physics-based coarse-graining, exploits scale separation, and this is something that you can sort of you then witness in how it describes chemical space. And so we have a simpler, coarser version of chemical space where we can more easily extract structure property relationships, which are coarser but give you a first idea, and we can also do some molecular design. And I'm at the end. Thank you very much for your attention.